Hello, and thanks for using TickBoom. In this question, we're told, without using the rational roots theorem, prove that there is no rational solution to the equation x cubed plus x plus 1 equals 0. And we're given a hint. Assume there exists a rational root and consider whether the left-hand side is odd or even. So this hint that we're given kind of tells us the technique we're going to use is proof by contradiction, because we're being told to prove that there is no rational solution, and we're told, step one, assume there is a rational root. So that is the technique of contradiction. You assume the opposite and then see whether you get a contradiction. Here we're told the potential contradiction we're going to have will have something to do with whether the left-hand side is odd or even. So that will be something for us to keep our eye out for. So if I just write what we're trying to do, so prove no rational solution to x cubed plus x plus 1 equals 0. And we're going to use contradiction, and step one to that, which we were told to do in the hint, is assume there is a rational solution, which I will call P on Q, where P and Q are integers with no common factors. So that is a way we can think about writing a rational number. It can be expressed in the form one integer divided by another, where those two integers have no common factors. Alright, so if that is a solution to this equation, then what that means is we should be able to substitute that in and it still hold true. So therefore what we can say is that P on Q cubed plus P on Q plus 1 is equal to 0. So all I've done is wherever there was x, I just put P on Q. So now let's kind of expand and simplify. So we'll get P cubed on Q cubed plus P on Q plus 1 equals 0. Let's try and get a common denominator, which I think will be Q cubed. So we'll get P cubed plus P times Q squared plus Q cubed, all on Q cubed. Hopefully you can see if you then divided the Q cubed through, you'd get this here. So that's equal to 0. Then I can multiply up the Q cubed and get left with P cubed plus P Q squared plus Q cubed is equal to 0. Now, given the right-hand side is 0, we can say that the right-hand side is, I'm going to describe this as not odd, since 0 is not odd. Now, I won't necessarily say 0 is even, because that's potentially controversial. I think there are good arguments for why you could say 0 is even. But to avoid that rabbit hole, I'm just going to say it's not odd. Our right-hand side is not odd, which means if our left-hand side is odd, then we've got our contradiction, and therefore we can draw our conclusion that there is no rational solution. Because if we assume there is a rational solution, we end up with a contradiction. So to kind of consider whether this left-hand side is odd or even, we need to think of cases. So, and it's all going to come down to whether P and Q themselves are odd or even. So, case 1, we could say, what would it look like if P is odd and Q is odd? So they're both odd. Case 2 would be, what would it look like if P is odd and Q is even? And then case 3 would be, what if P is even and Q is odd? And those are the three cases we need to consider. You may ask, well, what about P is even and Q is even? The reason we don't have to consider that is because if both P and Q were even, then they would both be divisible by 2, which means they would both have that common factor of 2. But we have said P and Q are integers with no common factors. So the case of P being even and Q being even is not relevant to our situation. So we just need to think about these three different cases, and if we can show that in all of these cases the left-hand side is odd, then we've exhaustively shown that there's a contradiction, and therefore this assumption can't be correct, so the opposite must be true. Now, in dealing with odd and even numbers, we'll kind of go back to first principles where we can say an even number can be written in the form 2 times m, where m is just some integer, and an odd number can be written in the form 2 times m plus 1. So that's kind of the basic building block of dealing with even and odd numbers. We're dealing with essentially the sum of three things. So we're going to need to consider what happens when you add odd numbers, or add even numbers, or add odd and even numbers. We've also got things to the power of 3 and to the power of 2. So we're going to want to think about what happens if you take an odd or an even number and do it to the power of 3. Is the result odd or even? What happens if you square it? Is the result odd or even? So what I might do is just systematically work through all of those scenarios with our basic building blocks here, and then we can use those results to then conclude what do we get with our left-hand side under each case. So first of all, I might just turn over. Let's think about what happens when you get an odd number plus an odd number. What do you get? So in that case, if we go to our basic format of an odd number, we'd have something in the form 2m plus 1 plus, and I might use a different integer, let's say 2n plus 1. That's what the sum of two odd numbers would look like. And that itself would be 2m plus 2n plus 2, since 1 plus 1 is 2. So I could write that as 2m plus n plus 1. So we've got 2 times an integer, since m and n are integers, so that's even. So if you take an odd number and you add an odd number, you get an even number. That's kind of result number 1 that we might want to make use of. If I take an even number plus an even number, that can be thought of as being in the form 2m plus 2n, which I can simply write as 2m plus n, 2 times some integer, also even. If I do even plus odd, which will be the same as odd plus even, the order doesn't matter here, we'd get something in the form 2m plus 2n plus 1. So that can be written as 2m plus n plus 1, which is 2 times an integer plus 1, and that is the format of an odd number, 2 times some integer plus 1. So that's odd. An even plus an odd gets you an odd number. Now let's think about our powers. So if I took an odd number and squared it, that would be in the format 2m plus 1 squared, which I could expand as the first one squared, so 4m squared, plus twice the product would be 4m, plus the last one squared, which I could write as 2 times 2m squared plus 2m plus 1. That's in the format 2 times some integer plus 1, so that's odd. So an odd number squared results in an odd number. What if we take an odd number cubed? That would be in the format 2m plus 1 cubed, which I could write as 2m plus 1 times 2m plus 1 squared. which I could expand as 2m plus 1 times this. So 4m squared plus 4m plus 1, which would be expanding this. 2m times 4m squared would be 8m cubed plus 8m squared plus 2m plus 4m squared plus 4m plus 1. So that would be 8m cubed plus 8 plus 4 is 12, so 12m squared plus 6m plus 1. So I could write that as 4m cubed plus 6m squared plus 3m plus 1. So that's odd. 2 times something plus 1, that's the format of an odd number. So an odd number cubed results in an odd number still. Okay, so that's an odd squared and an odd cubed. Now we want to see what do we get with an even number squared. So that would be in the format 2m squared, which would give us 8m squared, which is 2 times 4m squared. That's even. 2 times some integer. Oh, sorry, that would just be 4m squared. Sorry. 2 squared is 4, not 8. So that would be 2 times 2m squared, but still same outcome, even. So that even number squared gets us even. If we do an even number cubed, I think this is where my head was going to, we'd have something in the format 2m cubed. 2 cubed would give us 8. 2 times 2 is 4 times 2 is 8. M cubed, which we could write as 2 times 4m cubed, which is also even. So I think those are all the building blocks we're going to need to think about. If you add two odd numbers, you get even. If you add two even numbers, you get even. If you add an even and odd, you get odd. An odd squared is odd. An odd cubed is odd. Even squared is even cubed is even. Okay, so now what we can do is start working through our cases. So we'll start with case 1, which was P is odd and Q is odd. I'll just double check. I think that's the first one I defined. Yes, P is odd and Q is odd. So what would we get? So we'd get, if P is odd, we'd get an odd number cubed plus P is odd. So an odd number times Q is also odd. So another odd number squared plus an odd number cubed. So what does that give us? We just kind of go to our results. So an odd cubed is odd, so we get an odd number, plus an odd squared is odd, so we'd get odd times odd, and then odd cubed is odd. So what does that give us? An odd plus, now an odd times an odd is basically odd squared again. Odd squared is odd. So we get an odd number plus an odd number plus an odd number. An odd number plus an odd number is even. So if I just think about these two odds, if I add them first, I'd get an even plus an odd. And then an even number plus an odd number is odd. So the total result of our left-hand side when P is odd and Q is odd is an odd number, and that's our first contradiction. Because we're told that the right-hand side, we're not told, we can see that the right-hand side is not odd, yet when both P and Q are odd, the left-hand side is odd. So first contradiction. Now we want to see if we also get a contradiction in case 2 and 3. So case 2 would be P is odd, Q is even, and Q is even. So what will we get? P is odd. So we'll get odd cubed plus odd times even squared plus even cubed. An odd cubed is odd, as we saw from before, plus odd times even squared. Even squared is even, plus even cubed is even. So that's going to give us odd plus odd times even. Odd times even. Actually, I didn't do odd times even, so let's do that now. So if I had odd times even, that would be in the format 2m plus 1 times 2n, which would equal 4mn plus 2n, which I could write as 2mn plus n, so that's even. So when you take an odd number and multiply it by an even number, you end up with an even number. So this odd times even would be even plus even. Odd plus even gets us odd, so if I add up these two, I will get odd plus even, and then when I apply that same again, odd plus even equals odd. So even when P is odd and Q is even, in that case number 2, we've still got our contradiction. Now case 3, I think you could probably quickly guess we're going to get the same contradiction, because whether P is odd and Q is even, or Q is odd and P is even, it should be symmetrical. But for completeness, I'll just do it anyway. So we'll have P is even and Q is odd. So what we'll get there is we'll get even cubed plus even times odd squared plus odd cubed. Yes, that's right. P cubed, so even cubed plus even times odd squared plus odd cubed. So even cubed is even plus even times odd squared is odd plus odd cubed is odd, which equals even plus even times odd, same as odd times even, so we'll get even plus odd. This even plus odd will give us odd, so we'll get even plus odd, and then this even plus odd would get us odd again. So contradiction. So coming back to the core of our proof, we've been asked to prove there's no rational solution to this equation. We've assumed there is a rational solution, and in doing so we get to a result where we've got a contradiction because our right hand side is not odd, yet our left hand side is odd. So therefore what we can say now, and I might just have to, I'll just write it over here, therefore no rational solution to our equation, which was x cubed plus x plus 1 equals 0. And that is our proof by contradiction. So again, the proof by contradiction method, I think kind of how to start is often fairly straightforward. You're just assuming the opposite of what we're trying to show. This question actually told us that anyway as a hint. It also did hint to us that we were going to get to a place where we had to compare a left-hand side with a right-hand side and consider whether it was odd and even. I think where all the work came in this question was in coming up with these 3 cases and then kind of going back to first principles on odd and even numbers and just being very careful to kind of make sure you get to the right conclusions about all the combinations of odd and evens. So adding odds, adding evens, adding odd and even, and so on. And then from there we kind of can see, just working through very systematically, we get a contradiction every time. Therefore, we can conclude that what we were being asked to prove is actually true. So, yeah, hopefully you found that helpful, and tick boom.